Okay, so today's video is going to focus on categorical data. We'll explain obviously what that means as we move through the video. Remember, for time purposes, things will not be repeated a whole bunch of times. You will have a copy of the PowerPoint that you can be adding to as you move through the video. Remember to utilize your pause button, your rewind button, so that you can get what you need. But that way it'll keep our video from being 30 or 40 minutes long without the repetition within it. So let's start with some definitions. So when we look at a data table, our individuals are going to be the objects that are described by that set of data. It could be people, it could be animals, it could be things. There's a wide variety that it could be, and you'll obviously just need to look at your data table to determine what the individuals are. The variable is going to be the characteristic of the individual. And we'll look at this data table on the right here to kind of pick apart the differences between the individual versus the variable. And then there are two kinds of variables. We have what's called a categorical variable and a quantitative variable. Categorical variables place things in different categories, like color or location. Those would be categories that we could put something in, a type of something, like the different type of plant. A quantitative variable is going to take on a numerical value. Basically, a quantitative variable is something that you can measure. Height would be a quantitative variable. Weight would be a quantitative variable. So if we look at this data set on our right here, the first question is asking us who our individuals are. So take a second, pause, and read the paragraph here. All of our problems are basically going to be word problems. You can't skim them. You're going to need to make sure you actually read them, because when you answer the questions, you're always going to need to use context. And the context for answering the question is going to come from the question itself. So pause for a second, read the question. Okay, so hopefully you've read it, okay, and now we can answer these problems A, B, and C here. So the individuals in this particular data set, my individuals are going to be these 10 not randomly selected, these 10 Canadian students that completed the survey. Hopefully they were randomly selected. Okay, so those are going to be our individuals. So these 10 Canadian students. And then the variables that are measured are going to be all these things in the data table here. The province that they came from, the gender that they are, language spoken, handed, height, wrist circumference, and preferred communication. You'll notice that is a two-part question. It asks you to ID each as categorical or quantitative. So as we move through these, we need to determine, can I measure this, or were they sorted into a category? So these provinces, that's a category. Those aren't measurable. Gender, category, not measured. Language spoken, counting something is a form of measurement. So that the number, pay attention to, right, the fact that it says number of language spoken, that would be quantitative. Their handedness, that's going to be categorical, sorted into left versus right. Height is measured, so quantitative, it was measured in centimeters. Wrist circumference measured in millimeters, so quantitative. Preferred communication, categorical, sorted into one of those categories or not. And then part C here asks you to describe the individual in the highlighted row. So focused on this person right here. This is getting used to that concept of using context for all of our problems. All of your open-ended questions, at least one point is going to come from, did you do context of the problem? So if I'm describing that student, I would say that they live in Ontario. They are a male. They speak 4 languages. They're left-handed. They are 157.5 centimeters tall with a wrist circumference of 147 millimeters, and they prefer text messaging. Basically, I would put that row into a sentence. And if you did not already, I would pause, put that sentence into your notes as an example of this is how I would describe something. I would use all those context. And when I have a quantitative variable category, I would write the units. That's also part of my context. So as we start to explore data, one of the ways that we will do that is by looking at the distribution of the data. So the distribution of a variable is going to tell us what values that variable takes and how often it takes those particular values. And there's a couple of different ways that we can display that using what's called a frequency table. So a frequencies table can be set up based off of count. So for instance, this is categorical data. Our focus here again is going to be categorical data for this section. So there are these various categories that these different types of radio stations could be put into: country, religious, oldies, Spanish language, etc. This frequency table is just literally telling us the frequency. So how often do we see these stations? So for example, the religious station, 2014 of these 13,838 stations are religious. So that's just literally how many of them are religious stations. Another way to look at the distribution of the data, so how often the data is taking this particular value, is by looking at what's called a relative frequency table. When you see relative in statistics, you need to start thinking along the lines of percentages. Okay, and you can see how this relative frequency table is split into percent of stations. So this time, instead of saying the number of religious stations there are, we're looking at the percentage, 14.6%. And when we add up these percentages, we should get to about 100. You'll notice this is 99.9, right? And rounding errors and rounding is what would make that not be a perfect 100. So if you see that, again, this like 99.9, and you're asked to explain why it doesn't equal 100, again, that is just what's called a round off error. Once we have data sorted into tables, we can then move on to looking at graphs that will help display or show that data in a picture form, because sometimes that's a little bit easier than looking at the table. We have a couple of options for categorical data. We have pie charts and bar graphs. Pie charts are when you want to show basically the category's relationship to the whole. That's where a pie chart really becomes helpful. Remember, our whole circle will represent 100%. And so by looking at the various sizes of the pie, we can kind of get a quick visual of its relationship to the whole. When we look at a bar graph, each category is represented by a bar. And so when you're asked to draw these graphs, just like in AP biology or in chemistry or in physics, you have to make sure you've labeled that x-axis as well as that y-axis. And you'll notice the y-axis is going to have units. Okay? For instance, here I have percent of stations. It may just be number of stations, but those are a form of units. So in this instance, I graphed the relative frequency table here by putting my category on the x-axis and then the percent of stations that fell into that category onto the y-axis. Bar graphs give us a little bit more flexibility than a pie chart. I can use a bar graph to display the distribution of the categorical data. I can also use it to compare sets of data that were measured in the same way and using the same units. So let's take a look at this example here of what makes a good bar graph. So looking here with these MP3 players, here's our data set. Go ahead and pause for a second and read your background information. Okay, so hopefully you have your context now. So looking at our first problem here, part A, make a well-labeled bar graph to display the data. Describe what you see. So this is what your bar graph should end up looking like. So when we are making a appropriate bar graph, okay, it will not always say well-labeled. So any bar graph you make, you'll notice I've labeled the x-axis has been labeled with any units if there were units. So this was grouped together into years here. Okay, the y-axis has been labeled. Again, percent is a unit. So this is the percent of people within that age group that own an MP3 player. Okay, bars are consistent in their width, right? I have some bars that are wide like this and some that are skinny. Right, bars are consistent in their width, And then they match the data that we see in the table over here. For instance, percentage of people aged 12 to 17 years, 54%. Okay, I have a nice consistent scale on this x-axis, as on this y-axis, as well as spread out over that x-axis. So when you are asked to do the second part of this question, which is describe what you see, you want to look for trends, things that kind of stick out or are very noticeable, things that are what we would deem significant. I don't know if that's really the best word that I want to use here. So for example, in this one here, there is a much larger percentage of 12 to 17-year-olds that own an MP3 player. You could say that as generally as people are getting older, the percentage of people that own an MP3 player is going to be lower. Those are the things that you would talk about when you're describing what you see. Like I said, look for trends, look for highest, look for lowest. Those are the kinds of things you'll be putting into words, and we'll be practicing with that. Okay. The second one, part B, is asking, would it be appropriate to make a pie chart for these data and explain? Okay. Remember, we mentioned before that a pie chart is important as we look at components relative to a whole. And so this particular data set here, a pie chart is not appropriate. These are not percentages of a whole, right? I don't add all these up and they equal to 100. These are percentages from each individual age group. So a pie chart would not be a good representation here because they are not from a single whole. Okay, so take a second and let's look at this problem here, and then we'll look at this example. Okay, so for part A here, it says here's a clever graph of the data that uses pictures instead of the more traditional bars. How is this graph misleading? So it is not recommended that we use a pictograph. If you look here, the heights are appropriate. Oh, I can't draw a straight line, but the heights are appropriate. But the area of these computers, of these images, make it look like this Macintosh group is really, really high. Like way, way, way bigger than this none or these window groups, where it's really just a few hundred. Okay, so we need to kind of keep an eye on things like that, things that can be misleading because of the use of a picture there. You'll never see any good graph using a pictograph. Part B, two possible bar graphs of the data are shown below, so they're actually up here for space purposes. Which one could be considered deceptive and why? Okay, so if you look at this, if you look at the difference, you'll see the difference is coming here from this y-axis scale. And it starts at 0 on the graph that's on the left, and it starts at 10% on the graph that's on the right. So by changing where the scale starts, it can be misleading looking. It makes the PC group look really, really, really tiny, much tinier than it really is. And so it makes the relative percentages look much larger. Comparatively speaking, this Macintosh percentage looks much higher than the none and PC percentage than it does on this graph on the left. So it makes that comparison seem more extreme than it really is by affecting where the scale was started. So scale is something that we'll really need to keep in mind when you're designing a graph. Is your scale appropriate for that data? Does it allow you to really accurately look at the data and, describe it and make comparisons with it? All right, so let's look at a different kind of table here called a two-way table. So a two-way table is going to involve two categorical variables. So if you look at this table here, you'll see how this table has young adults by gender and chance of getting rich. So their opinion on their chance of getting rich, that is one categorical variable. And then sorted by gender is another categorical variable. So this is called a two-way table, and you can look at distributions amongst these different variables using this two-way table. So one of the kinds of distributions we look at is what's called a marginal distribution. So a margin, right? They're going to be on the edges here. That's why it's called our marginal distribution. So the marginal distribution of one of the categorical variables in the two-way table is the distribution of values of that variable among all the individuals described by the table. So for instance, let's come down here and look at part A. Part A says use the data in the two-way table to calculate the marginal distribution in percent of opinions. So I'm taking one of the categorical variables, opinion, and I'm going to look at the distribution of the values for that particular variable amongst all the individuals described in the table. So for example, for part A here, let's go with the no chance. I have my total for no chance is 194, and my total for the whole table here is 4,826. So the marginal distribution there for almost no chance is, I multiply it by 100, is 4.0%. And I can do that all the way down. For example, let's come to the 50-50 chance, right? So I've got 1,416 over my total for the whole table times 100, so I can get my percentage there, and I get 29.3%. And this is considered my marginal distribution because these distributions would end up out here in the right margin and down here on the bottom. For instance, I could do female, my distribution of females here, so it'd be 2,367 over 4,826. So for part B here, it says make a graph to display the marginal distribution and go ahead and describe what you see. So if I'm making a graph to display the marginal distribution, I would need to have go ahead and calculated every single one of these. I'm just going to calculate 3 of them. So let's calculate almost certain. So 1,083 over 4,826 and times 100, which will give us 22.4%. So I have a start here of data that I can start to put into my graph. So deciding what kind of graph this would be, because I have categorical data here, I'm going to draw a bar graph. So I would have my categories down here on the x-axis, right? Almost no chance. I'm just going to do the 3 that we had, 50-50, and almost certain. You would not abbreviate these, but due to my writing utensil that I have here, you want me to abbreviate them. You won't be able to read it if I don't. Okay. I need to title this whole axis. So I need to say that these are my survey response or my opinion of how rich they would be. And here's my 3 different categories that I measured. I calculated percent. So I need to make sure I label my y-axis. And then I need my nice consistent scale over here on the side. So let's go 5, 10, 15, 20, 25. Okay, and then I would just draw a bar graph for this. So my almost no chance is 4%. My 50-50 is 29.3. So up there near the top. Oops, that's not a good straight line. Okay, and then 22.4. So right about there. Okay, and my bar graph would be all set there. Okay, and I'm not done though, because my question asked me to describe what I see. So I would want to take a look at that, if there's any extremes, if there's anything that's close to the same. For example, if we had calculated out all 5 of them, a lot of young people are pretty optimistic about their, there's high numbers of them that think they're going to be doing pretty well. There's about the same number of them that said 50-50 chance versus good chance. Over half of them think that there's a good chance or almost certain that they'll be rich by the age of 30. So there's a lot of ways that you could describe this. But again, those are the things that you're looking for. Trends, things that are really high, things that are really low, being able to compare things together. So our next kind of distribution is what's called a conditional distribution. So a conditional distribution is going to have a condition placed upon it. So I've got a variable, describes the values of that variable among individuals who have a specific value of another variable. So there's a separate conditional distribution for each value of this other variable. So for instance, okay, so this example here, calculate the conditional distribution of opinion among the young men. So my condition here is that I'm only looking at the young men. And so now I'm going to look at their distribution of their various opinions. So now, instead of looking at the total for the whole table, like I did for marginal distribution, because marginal distribution of almost no chance took in both males and females, I'm only looking at males. So 98 out of 2,459. And that will give me my conditional distribution of males that feel that they have almost no chance of being rich by 30. Let's look at the almost certain chances by 30, right? So again, the condition is that they're males. So I'm only looking at the total for the male population. And then for each opinion, so if I'm looking at the almost certain opinion, now I get 24.3%. And you could do things like calculate these for females as well, and then do comparisons and that kind of thing with your descriptions for that. So that's how you would calculate a conditional distribution. Instead of taking it out of the whole table, you take it out of the population that fits that condition, in this case being a male. Okay, so let's look at this example here. Go ahead and take a second and read the question, look at the two graphs, and start thinking about how you think you would approach this question. Okay, so based on the survey data, can we conclude that young men and women differ in their opinions about the likelihood of future wealth? So, and it asks us to give appropriate evidence to support our answer. So we're looking at this, we've got two kinds of graphs here. This first one here is called a side-by-side bar graph. So basically what we did is we took the conditional distributions of females, are the blue bar, and the conditional distributions of males are the red bars. And then we just put them side by side so we could look at them, side by side. So when we're asked here if we can conclude that young men and women differ in their opinions, looking at this, we would say that, yes, they do. And we would go, our evidence that would support some of this would be the fact that males seem to have a higher opinion of their ability to be rich by the age of 30. Looking at, there's a higher percentage of males that believe they have a good chance and an almost certain chance than females. Now, when we're asked to give evidence, just saying higher isn't enough. We would want to, even if it's just in parentheses, writing something like the two values and just comparing them to one another, right? So just, stating that in a good chance, there's 30.8% of males versus 28% of females, kind of thing. So not just stating more males or less females. And we could also use the evidence from the, some chance and the almost none, that the percentages of females that believe they will be rich by the age of 30 is higher in the categories in the opinions where they believe they will not. This other graph over here on the right that was used to compare the data, this one is called a segmented bar graph. And so with a segmented bar graph, you'll notice it requires a key. And again, it allows for comparisons. Okay, each of the opinions is a different color in this case. It could be a pattern if you didn't have color. And they are just graphed by color. What you need to realize is that they're not always starting from 0, right? The whole bar here adds up to 100, like a pie chart almost. And the bar is segmented up. So for instance, with females, the percentage of females that was almost none is 4.1%. And then the percent that is some chance is 18%. So this actually on our scale is running from 4 to about 22 but this whole block here is worth 18%. Okay, and so we would keep going up our segmented bar graph like that. So we could use that one as well. I feel like a side by side is a little bit easier to compare with than a segmented, unless there's very large discrepancies there. But again, I just want to be clear, when you're asked to do things like give and describe, one word answers wouldn't cut it, right? You couldn't just say yes and then be done, right? You would say yes and give your values, use your context, and we will be practicing this a lot in class. Okay, let's look at one other type of graph here called a mosaic plot. So a mosaic plot is just a modified segmented bar graph. So you can see here how these bars are broken into segments, but you'll notice they're broken into segments both going up and down, as well as right to left, from side to side. So a mosaic plot is a modified segmented bar graph in which each rectangle, the width of the rectangle is proportional to the number of individuals in that corresponding category. Okay, so I know I said I wasn't going to repeat, but let's make sure you got that down, right? Modified segmented bar graph, the width of each rectangle is proportional to the number of individuals in that corresponding category. So let's look at this data table here from the Titanic. So this is based off the Titanic here. And so how we're broken up here is whether they survived or not. So that's one category, survival. One category is gender, male or female. And then the third category here is kind of what part of the ship they were. Were they first class, second class, third class, or part of the crew? So if we look at this mosaic plot here, the class is down at the bottom. So there's our class. So you'll see it's proportional to how they were divided up. So the smallest proportion was first class, then second class, and then a larger percentage of the passengers were third class, and the largest were part of the crew. So that's why those rectangles are different widths. And then it's broken up here on the side by gender. And then that gender is broken up to whether they survived or not. So for instance, this rectangle right here represents the chunk of male first class passengers that did not survive. And then here's your male first class passengers that did survive. Okay, same down here, like you could look at females. So here's our percentage of females that survived that were first class on the Titanic versus female crew members who survived that were members of the crew. I don't expect you to be able to draw mosaic plots. The questions that are surrounding mosaic plots would be more around interpretation, and we will work with these in class. What you just need to realize is that I've got a modified segmented bar graph here. So you're looking at these different proportions. The one on the right is showing if the proportions were independent, meaning if it didn't matter what class of passenger you were or part of the crew, and it didn't matter if you were male or female, where you can see on the left, it did matter. It did matter if you were which member of the ranking class you were, as well as it definitely mattered if you were male or female. It impacted your survival. So on that note, this is the last thing we're going to look at today. We're going to look at what's called association. So association between two variables is knowing if the value of one variable helps predict the value of the other. For example, we just saw that in the Titanic example. The knowing the gender, so male or female, helped predict survival. Knowing class, first, second, third, or part of the crew also helped predict survival. If knowing the value of one variable does not help you predict the value of the other, then there's no association. We're not going to say they're independent right now because we're going to have different criteria that meets that independent category, but we're just going to say that there's an association or there's no association. So pause for a second and look at these three questions, and we'll run through this example very quickly. What would really be ideal is if you went ahead and tried to solve this problem and you're more checking your solutions. All right, so let's look at number one. I'm not going to do every single one of these. It would be amazing, and you should do every single one of these, and you can welcome to check your answers in class. But again, for time purposes, I'm not going to do every single one. So I'm looking for the conditional distributions of superpower preference among students from the UK and the United States. So that's my condition, the ones from the United Kingdom, and then the ones from the United States. So one of the first things I would need to do is I need a total of how many I have from the United Kingdom. So I have a total of 200, and how many I have from the United States, and I have a total of 215. So for instance, let's look at fly. So my conditional distribution for the students that would choose fly from the UK is 54 over 200. Okay, and that is going to give me 27%. And if I did it for the US, let's say I did super strength for the US, 23 out of 215, because I'm only looking for the US, and that would come out to 10.7. And that's how I would look at my conditional distributions. Again, remember, if I was doing marginal distributions, I would, like, for instance, if I wanted the marginal distribution of flying, I would have 54 plus 45 over my total, over my 415 students. That would be for a marginal distribution because there's no condition based upon them. Okay, so for this question, to get full credit on this question, you would have 10 answers. All 5 different categories for UK, all 5 different kingdoms for the United States. This next one asks to do an appropriate graph to compare the conditional distributions. So if I'm looking to compare these two distributions, I'm not going to use just a plain bar graph. I'm going to use a side-by-side bar graph, or I could use a segmented bar graph. Whichever one I choose to use, I need to make sure, wow, I can't draw a straight line. I need to make sure that on my x-axis, I'm being very clear what's down there. So I need to label my superpower. I'm doing conditional distributions, so percent on the y-axis, nice consistent scale, and I would need some kind of key. If I was doing a side-by-side, then I would just need to somehow indicate which ones were US versus which ones were UK. If I was doing a segmented bar graph, I think when I wrote like that, I think it went off the edge. If I was doing a segmented bar graph, I would need a key also for each different area of the bar. So for instance, side by side, I could say that the bars that were US were red and UK were blue. If I was doing segmented, remember, if I'm doing segmented, my bar is divided into a number of areas, and each one of these areas would need to be represented in the key as to what category it was, whether it was flying, freezing time, invisibility, super strength, telepathy. For number 3 here, is there an association between country of origin and superpower preference? Give appropriate evidence to support your answer. Okay, so for this one, as we've gone through and calculated all your conditionals, you would say that there is an association between country of origin and superpower preference. That is me using my context. So there is an association between country of origin and superpower preference. And then my evidence is going to come from my numbers and my graph. Students in the UK are more likely to choose flying and freezing time at 27% for the UK versus 20.9% for the US, and 26% for the UK for freezing time versus 20.5% for the US. So that would be evidence that more students from the UK are choosing those two powers, but more students in the US are more likely to choose invisibility and telepathy. And again, I could cite my evidence, right? 17.2% for invisibility in the US versus 15% for UK as well as 30.7% for telepathy for the US versus 22% for the UK. So again, I'm describing what I see. I'm putting what I see and what I calculated into actual words. And we'll do lots of in-class practice with this.